All right, so we have this problem for Atwood's machine. We did the first one in class, and then we're going to focus on question number 2. So it says, for the following system released from rest, determine the acceleration and the time of mass 2. Use G for 9.8. What is the coefficient of friction between the table and the block? So there's a lot to unpack here. We kind of have to solve for several things. So we're looking at this Atwood's machine. I already know that my tensions in both strings will be the same. So T1 is equal to T2. So because of that, I'm going to use the variable T for it eventually. I'm just gonna divide it out into 1 and 2 just to keep things clear. And then acceleration of both blocks will be the same. So as this block travels down, this block will travel to the right. And they're gonna accelerate in the same rate. So I went ahead and drew my free body diagram. So one thing to know about my free body diagram was that there is subscripts to indicate that these are for these values. Okay, so these are for block 1. And then there is forces for block 2. So we're going to label block 1 and find the forces in the x direction for block 1 and the y direction. And then we're going to do the same thing for block 2. So block 2 will have the same method, forces in the x and the y direction. But the thing about block 2 is that there are no forces in the y direction, so we can just get rid of it, okay? I mean, there's no forces in the x direction, so we can just get rid of it. So let's go back to block 1. So block 1, looking at this, I'm going to see which acceleration I need to find. So that's my first question, determine acceleration. So if I need to determine acceleration, then which one do I do, right? So the block, I know it's going to be traveling to the right. It's not going to be traveling up and down, so that means my acceleration in the y direction will be 0. So in the x direction, I also see that it's going to be traveling in the positive direction. So my acceleration should be a positive acceleration. So let's look at my forces in the x direction. We have these two. So T1 is going in the positive direction minus force of friction is equal to mass times positive acceleration. So I can expand this and say that T1 minus mu times force normal 1 is equal to ma. And then in the y direction, I'm going to do this over here. So it's going to be slanted a little bit. We have force normal and force of gravity for block 1. So force normal, Fn1 minus f of g1 is equal to 0. So I can expand this and say that f of n1 is going to be equal to m1g, and that's really because I move force of gravity to the other side. Okay, and I replace mg for f of g. So from here, I know that eventually I have to solve for acceleration. Okay, so that means I need to have every other variable. I generally have every mass. I have mu. It's given to me right over here. Actually, mu is not given to me. That's crazy, right? So, but we'll get to that. We'll get to that obstacle when we get to that. So from here, we have our acceleration. So our acceleration is going to be right here. So we need to find our value for f of n, which we just solved for. We'll plug it in right over here. Okay, so T1 minus mu times m1g is equal to ma. Okay, so we have almost everything. M1A. So I know that I'm going to have to solve for tension. So whenever I solve for tension, it's going to be m mu times m1g plus m1a. So this is going to be my tension because I'm eventually going to set the tensions equal to each other because T1 is equal to T2. And then let's go into block 2. So block 2, we have the y direction. So we have T2 minus f of g2 is equal to acceleration in the y direction. So in this case, this object actually is traveling up and down. It's going to be going downwards. So since it's going downwards, whoops, force of habit, mass 2 is going to be multiplied by acceleration. Okay, so acceleration in the y direction is the same thing as the acceleration for block 1. So I'm just going to have a. So from here, I'm going to solve for T2. I'm going to replace f of g2 with mg. But let me backtrack real quick. So let's look at the direction of this acceleration. So when we look at the direction of this acceleration, I know that this object is going down. So because this object is going down, acceleration is going down, then that means my acceleration here is going to be a negative acceleration. Okay, so m2 is equal to m2g minus t2. Okay, so from here I'm going to solve for t2, and that's going to be equal to m2g minus m2a. And you might think like, oh, why do I have to put that negative in there, right? So usually whenever you are using the UAM equations in the first unit, usually your answer either came out negative or positive and it gave you the direction. But in this case, we're dealing with two objects in a system, so we have to predetermine the negative or positive. So it won't automatically tell us because we're trying to look at the interactions of two blocks with each other. Okay, so usually in kinematics it would tell you, but here not so much. We're not really doing kinematics yet. Okay, so now we're going to look at these tension values that we found, and we're going to set T1 equal to T2. So whenever I do that, I should get mu m1g plus m1a is equal to m2g minus m2a. So looking at this, I want to solve for acceleration. So whenever I solve for acceleration, I'm going to get my acceleration onto one side. So my terms of acceleration should be going to one side. So I'm going to add m2a to both sides, and then I'm going to subtract mu m1g on both sides. Mu m1g. Okay, so from here I should have, oops. Okay, so from here I should get m1a plus m2a is equal to m2g minus mu m1g. So if you notice, mu just affects block 1, which is going to be the one that is going to be rubbing on the table. So I'm going to factor out acceleration. So m1 plus m2 is equal to, and I'm going to factor out g as well because it makes it look cleaner, m2 minus m1. So if I were to solve for acceleration, then I have m1 plus m2. Okay, so these cancel out. Same thing over here, m1 plus m2. So that is my resulting acceleration. So acceleration is going to be equal to g m2 minus m1 over m1 total mass, okay? So that's going to be very reminiscent to the acceleration of the system is equal to the net force over the total mass, okay? So this is total mass. The net force would have been gravity, mostly m2, so the mass of block 2. We're going to subtract that from the mass of block 1. Okay, so generally speaking, this is very similar to the f of g equation, okay? And that would be the weights of the block, okay? All right, so from here, I'm gonna go ahead and try to solve for acceleration, but we still have that problem of not really having, oh wait, I forgot to have mu in this situation. So I left out my mu somewhere. Poor Mew. Mew like my cat. Mu should not be forgotten. So let's bring that back. Let's bring mu back. Hey, mu. Okay. So from here, I basically have everything. I do have the mass of blocks, gravity, but I don't have mu, right? So from here, I can use, so to find mu. So I know my equation, force of friction, is equal to mu times force normal, right? So do I have force of friction? Absolutely. So force of friction is given to me over here. So I'll just use that 20 newtons is equal to my mu, which is needed to be found. And I do have an equation for force normal. So force normal is just the mass of block 1 times g. So we have force normal being equal to the mass of block 1 times g. So we've derived this equation. So whenever we derive this equation, I know that my m1g should be placed in here. So now I'm going to do 20 is equal to mu, mass of block 1 is 7 times 10. So as a result, mu is going to be 2 over 7 whenever I find this algebraically. So whenever I find mu, it should be 0.29, okay? So if I were to solve for acceleration, I'm gonna put this value over here. Whenever I solve for acceleration, I should get 10 mass 2, which is 3 and 7. Okay. 3 minus mu, which is 0.29 times 7. So mu is very important. If we didn't have mu, then my acceleration would have been, it would have ended up being a negative value. And that's, I mean, it's not technically wrong, but we don't want that, you know? Okay, so 3 plus 7 would be the masses. So right off the bat, I have my answer being 0.97 meters per second squared, okay? So I already found two of the 3 things that I was supposed to find. I found mu, I found acceleration. Now I have to find the fall time. So the fall time for mass 2 should be the same as the movement time for mass 1. So there should be 1 time that we're solving for. So we're gonna solve for time. Don't worry about whatever this is. Solve for time. So UAM equations. So let's just say distance, d initial, d final. Okay, well, if we're looking at block 2, then it would be y technically, and then v, a, t. Okay. So the height at which this block will travel is going to be 0.9. So it goes from 0, or whatever it starts at, to 0.9 meters. So it's going to travel in this direction, and we're just going to say that it goes from 0 to 0.9. And then velocity, initial velocity should be 0 because it comes from rest. And then final velocity, we don't have acceleration, we just solve for, so it's 0.97. Time we're trying to find. So time, I derive that equation from this equation. Change of x is equal to v initial times time plus 1/2 at squared. So time would have been the square root of 2 times x over acceleration, given that my initial velocity is 0. So from here, my square root of 2 times 0.9 over acceleration, which is 0.97. And I made, not really a mistake, but change in direction in the y direction. So from here, my time is equal to 1.36 seconds. So that's how long it takes for the block to travel down. Okay, so that's the question for the Atwood's machine. Let's move on to the pulley machine. So with the pulley machine, we did this problem on Thursday, but we didn't entirely finish it. We just got to deriving the equation here. So for number 4, we just looked at this Atwood's machine being released from rest. We found the acceleration, and then I forgot to plug in values for the acceleration, and whenever I plugged in those values, I got 2. And then from here, I use my 2 for my UAM equations. So you can definitely take some time to look at the PDF that I'm going to be posting on Google Classroom. Let's go to number 3. So number 3 is, it can be daunting because you see that there's a hand here pulling at this. So you're like, oh my gosh, I have never done this before. But anything can be solved whenever you use the free body diagram method. So it's asking you, what does the Newton scale read if the system is at rest? So if it's asking about the Newton scale, I'm going to label this as the force of the scale. So let's go ahead and draw our free body diagram for mass 1. So mass 1 has some sort of tension 1, and then mass 1 also has a force of gravity, F of G, for 1, and then also has an additional force, which is going to be force of this scale, so that dude. So block 2 will have something similar, but it won't have the force of the scale. So block 2 is going to have tension 2, and then it's going to have F of G 2. So from here, we have to determine if this object is going to move. So we already know that it's going to be at rest. So since it's at rest, there's no acceleration. Okay, so that just makes our life so much easier. There's no acceleration in the x or y direction. But we can still use our sum of forces method. So this is for block 1. And my goal here is to find the force of the scale. Okay, So I need to use my forces. There are no forces in the x direction, so we can just do away with that. So forces in the y direction is equal to mass times acceleration. But there is no acceleration. So this side becomes 0. We can do that with block 2 as well. So whenever we do block 2, sum of forces in the y direction is going to be equal to 0. So in the y direction for block 1, we have T1, which is positive, minus f of g1 minus f of the scale is equal to 0. Block 2, T2 minus f of g2 is equal to 0. So from here, my goal is find f of the scale. So I'm going to, I could either just solve for f of the scale, but that just leaves me with tension, and I don't really know what to do with tension. But I know for this problem, T1 is equal to T2. So tensions are equal to each other. So because they're equal to each other, then I can solve for tension. So tension 1 is going to be equal to f of g, I'm just going to expand it to m1g, plus f of the scale. Okay, so I'm going to do that. And then T2 is going to be equal to, I'm going to expand it to M2G. So from here it's pretty simple. So we can say that our tensions will be equal to each other. So whenever our tensions are equal to each other, we can set T1 equal to T2. So M1G plus f of the scale is equal to M2G. So from here, I can just solve for the scale M1G. I'm going to move M1G to the other side. So then I'm left with f of the scale is equal to M2G minus M1G. And look how easy that equation looks, right? So f of the scale will end up being, so mass 2 is going to be 6 times 10 minus mass 1, which is 4 times 10. That is 60 minus 40. Oh my gosh, that is so easy. Okay, so the amount of force that this guy needs to pull in order for this whole system to stay at rest is going to be 20 newtons. Pretty easy peasy. It might look a little bit different on my PDF file because I made the mistake of not setting my acceleration equal to 0. So I said in my notes, I forgot the question stated that the system was at rest, so I went back and substituted acceleration for 0. So I did way more work than I had to. All right, bye, have a good night.